In the last few videos, we've been discussing how you can experimentally measure chiral molecules in a laboratory using plane polarized light. The assumption in all of those exercises, though, was that you only have one chiral center. You only have one hand. So you either have all your molecules are the right hand of the version of the molecule, or all your molecules are the left hand version of the molecules. Now, the right and left hand versions of molecules that are the same in everything except their right hand and left hand versions switch, those molecules have a special relationship. They're not the same, like your left and right hand aren't the same, but they're really, really similar. So there's a special word that describes that special relationship, and that special word is enantiomer. So the left and right hand version of a molecule, the R and the S version of a chiral center, those are called enantiomers. The relationship between those two is that they are enantiomers. Enantiomer was a word like cousin or friend. It describes a relationship between two things that have a special relationship. So we talked about last time how if you have plane polarized light and you shine it through one enantiomer, it will rotate the plane polarized light a certain number of degrees. And if one, so let's say 10 degrees, if one enantiomer, let's say the R version of the hand, rotates the light to the right 10 degrees, then the other enantiomer, the left-handed version, will rotate the light in the opposite direction to the left the same number of degrees. Now, I want to emphasize these two things aren't always connected. So, for example, the R enantiomer doesn't always rotate light to the right. Sometimes it rotates it to the left. And the S enantiomer doesn't always rotate light to the left. Sometimes it rotates it to the right. But whichever way the R rotates the plane polarized light, the S will rotate it in the opposite direction, the same number of degrees. So before, we were just thinking about having one of these enantiomers, the R or the S hand for each of the chiral centers, and that enantiomer rotating the plane polarized light. But what happens if you have a mixture of these two? Let's think first about the simplest type of mixture you could have. What if you had 50% R and 50% S? That mixture has a special name, and that name is going to come back. That's called a racemic mixture. This will come back in future chapters. That's a racemic mixture when you have a 50-50 mixture of the two enantiomers, the right-handed and left-handed molecules. So, if you have a racemic mixture, well, the right-handed, the 50% of the solution is going to want to rotate light 10 degrees to the right. The other 50% is going to want to rotate it 10 degrees to the left, and ultimately it would cancel out, and you would get no rotation of your plane polarized light. In order for you to have some sort of rotation, you have to have more of one enantiomer than of the other. In other words, you have to have one enantiomer in excess. So, for example, let's say you had 70% of the R. So this is a different case. This is not a racemic mixture. Let's say you had 70% of the R and 30% of the S enantiomer. Well, in that case, you can think of this 70 as having sort of two parts. You can think of it as having a part that's like 30%, and another part that's like 40%. And actually, let me do this in colors. So we have 70% of this R enantiomer that wants to rotate the plane polarized light to the right, and we have 30% of this S enantiomer that wants to rotate the plane polarized light to the left, 10 degrees. So you can think of this, the R, the 70%, as being in two parts. One part is 30%, and the other part is 40%, and you add those up and you get 70%. Now, if you think about the 30% of the R with the 30% of the S, a similar thing will happen as happened with the racemic mixture. They cancel each other out. This 30% wants to rotate the light to the right a certain amount. This 30% wants to rotate it to the left a certain amount, and they cancel each other out. But in this case, unlike in a racemic mixture, the plane polarized lights will still rotate because there's some of one of the enantiomer left. There's some of that R enantiomer left, and so it will still rotate light to the right. Now, it may not be a full 10 degrees, but it'll still rotate it a little bit to the right. And so you have some of one enantiomer in excess. You have a percentage of one enantiomer in excess. And the way to talk about that symbolically is we have an enantiomer, E, in excess, another E, and we have the percentage for it. And we can tell how much of the excess we have because that enantiomeric excess will be measured by, you can measure that by how much the light, the specific rotation of that light moved over in the mixture. Here we only have 40% turning it, so in this mixture of stuff, it's only going to turn it as if there were only, it's going to turn it less because there's less that's really making it turn. Compare the mixture to the specific rotation for that same molecule, pure. So what if it were 100%? How much would it rotate the light? And then compare, given what it is, how much it did rotate it, and that will give you a sense of how much more of one enantiomer you have than of the other. And just to get a percent out of that, you'd multiply that by 100. So notice this enantiomeric excess does not tell you how much the percentage of what the enantiomer that you have. It tells you how much more you have of one enantiomer than of the other. So the enantiomeric excess for this scenario that we had above, the enantiomeric excess would be 40%. We have 40% more of this than of the other. But notice in the mixture we had 70% of the mixture as that enantiomer. So this is a new haiku. This is a new equation that relates things in a succinct way. And the key word that you would see that would want to remind you of this equation is %EE. If you see that instantly, write down this equation. So remember our procedure. Our procedure here was anytime you see a lot of numbers, a lot of words, scan the question looking for a keyword. Don't try to understand the entire question all at the first sight. Look for a keyword, you'd see your %EE, write down the formula, and then anytime you write down the formula, write down each of the variables in the formula separately, so that as you read through the problem, you can organize the information that you come across. So it says here, the specific rotation of L-dopa, this is a drug that's used to treat Parkinson's disease, in water, and notice it has a specific rotation, which means it's chiral. In water, and they give you a temperature, notice the temperature is not here, it doesn't matter, at 15 degrees is negative 39.5 degrees. Now this is for this pure compound. So the specific rotation for the pure compound is negative 39.5 degrees. It says a chemist prepared a mixture, now we're talking about the mixture, of L-dopa and its enantiomer. And this mixture had a specific rotation of negative 37 degrees. And they want us to find the percent enantiomeric excess. So we just plug it into this formula. The percent enantiomeric excess equals the specific rotation of the mixture, that's negative 37, divided by the specific rotation of the pure compound. So we can see that the pure compound rotated the light more than the mixture. And the amount that the mixture rotated, it depends on how much of that was in excess, how much of it didn't get canceled by the other enantiomer in the mixture. And to make it a percent, we just multiply by 100. So if you plug that formula into a calculator, you'll have negative 37 divided by negative 39.5. And so that's going to give you around 93.67%. 93.67%. Now, just so we can talk about numbers a little more easily and think about this conceptually what this means a little bit more easily, I'm going to round this up to 94. Now, you could leave it as 93.67 in an answer on a test, but just so we can talk about what this means, I'm going to round it up to 94. This does not mean that the mixture is 94% L-dopa. This means that you have 94% of L-dopa left after the other 6% cancels itself out. You have 96% more, or you have 94% more L-dopa than the other enantiomer. So we've used 94%. There's another 6% of stuff that's there. This is like 94. There's still another 6%. That 6% got canceled out. Otherwise, it would have rotated the light. And so, here, let me put this in green. This is our 94%. The other 6% canceled itself out, and the only way it could have canceled itself out is if 3% was one enantiomer and 3% is the other enantiomer. Then, one makes the light want to rotate in one direction, the other makes it want to rotate in the other direction, and they end up canceling each other out, so you only have the 94% rotating the light. In other words, this enantiomeric excess is not giving you the percentage of L-dopa in the water. It's giving you how much more L-dopa there is than the other enantiomer. And that would be 94%, and that's 94%. The percent of L-dopa in the water would be 94% plus the percent that's getting canceled out. This solution would be 97% L-dopa. So I just wanted to clarify that. Enantiomeric excess tells you how much more of one enantiomer you have than of the other, not the absolute amount of the enantiomer that you have. So now that we've discussed that concept in some detail, we can do these other problems a little faster. So you'd scan this problem, you'd see the key phrase percent EE, percent enantiomeric excess. You paste or you draw out this formula, and anytime you have a formula, write each of the variables in the formula separately so that as you read through the problem, you can organize the information that you come across. So the first number we see is a specific rotation of ephedrine, this medication, is negative 6.3. Now this is just ephedrine, so that's the pure compound. Rotates light, plain polarized light, 6.3 degrees to the left because it's negative. It says a chemist prepared a mixture, so now we're talking about the mixture of ephedrine and its enantiomer, and this mixture had a specific rotation of negative 6 degrees. So the mixture rotated light only 6 degrees to the left. We want to know how much more of that dominant enantiomer we have in our mixture. So what's the percent EE? Well, the percent EE, percent enantiomeric excess, is equal to the specific rotation of the mixture, so that's 6, divided by the specific rotation of the pure compound, 6.3 times 100. The pure compound would have rotated this a lot. We rotated it less. That's because the other enantiomer is canceling out the rotation from some of the ephedrine. And so we take negative 6 divided by negative 6.3, multiplied by 100, and I'm getting around 95.24%. So 95.24% of ephedrine as the enantiomeric excess here. That means that we have 95.24% more ephedrine than of the enantiomer. That is not the absolute amount of ephedrine in the sample. To get that, you'd have to get the rest of this, take 100, subtract this, divide it by 2, and to add it to this, like we did in the previous problem. Take the rest, divide it by 2, and add half of it to the percent excess. Okay, but the enantiomeric excess for ephedrine in this problem is 95.24%. We have that much more of one enantiomer than of the other in our mixture. So likewise here, you see the key word %EE. So you write down this formula. Not only that, but you take each of those variables and you write them separately so that as you read through the problem, you can organize the information that you come across. So we're looking at a solution of vitamin B7, which is chiral, and it says that the specific rotation of pure B7 is positive 92 degrees. So pure vitamin B7 will rotate plane polarized light 92 degrees, and it's positive 92 degrees. So it'll rotate plane polarized light 92 degrees to the right. Now it says the chemist prepared a mixture. You have vitamin B7 and its enantiomer, so now we're talking about the mixture, and the specific rotation for that was positive 85. So notice it's not rotating the plane polarized light as much because the other enantiomer is canceling out the rotation coming from some of the B7. They want to know how much more of the B7 we have than of the other enantiomer. So the percent enantiomeric excess is the percent of the mixture, the rotation of the mixture, which is positive 85, over the rotation of the pure compound, which would be positive 92, and then we multiply by 100. So notice the mixture is not rotating the light as much as the pure compound would have, because not as much of it is in excess. So the percent EE here will be, the percent enantiomeric excess will be 85 divided by 92 times 100, I'm getting around 92.39. So that'll be 92.39% more. You have 92.39% more vitamin B7 than its enantiomer. Notice, this is how much you have more than of the other one. It's not the absolute amount of vitamin B7 in the solution. Finally, for this last one, similar thing. You see the key phrase %EE. That's telling you that you use this equation, you write the variables in this equation down, %EE, so that as you read through the exercise, you can organize the information that you come across. And we have L-alanine here, which is an amino acid used to make proteins. They say the specific rotation of just L-alanine, pure L-alanine, is positive 2.8. So this is dextrorotatory. It's going to rotate plane polarized light to the right 2.8 degrees when it's pure. It says a chemist prepared a mixture, so now we're talking about our mixture of L-alanine and its enantiomer, and 3.5 grams of the mixture was dissolved in 10 milliliters of water. The solution was then placed in a sample cell with a path length of 10 centimeters, and the observed rotation was positive 0.78 degrees. Now the observed rotation is not what we have here. The observed rotation doesn't have the brackets, as we talked about in previous problems. But the observed rotation does relate to the specific rotation. And so that key word, observed rotation, is a sign. That, combined with the knowledge that we need the specific rotation, that's a sign that we have to use the equation we used in the previous problem. Namely, that the specific rotation, which is what we want, the specific rotation of the mixture is going to be equal to the observed rotation of the mixture. That's the alpha without the brackets divided by the concentration times the path length. So, for this, we have several variables. We've got the specific rotation, that's what we're looking for. Once we have that, we can plug it in here. We have the observed rotation. We have the concentration, and remember that's got to be in grams per milliliter. And then we have the path length, which remember has to be in decimeters. So we have 3.5 grams, that's going to go in the concentration. we have 10 milliliters. That's going to go in the concentration. We have a path length of 10 centimeters. Remember, that's equal to 1 decimeter. And if this is confusing to you, go back to the exercises for 512, 513, and 514. So they gave us the path length of 10 centimeters, which we know is 1 decimeter, and they gave us the observed rotation, which is positive 0.78. So we can get that the specific rotation by plugging these numbers in. We have 0.78 for the observed rotation. The concentration we have, 3.5 divided by 10, that's 0.35. And then the path length is 1 decimeter. So the specific rotation will be, for the mixture, will be 0.78 divided by 0.35. I'm getting around 2.23. So 2.23. So the mixture here would rotate light to the right 2.23 degrees. So that is the specific rotation for the mixture. So we had to use this specific to observed rotation equation to figure out this specific rotation of the mixture. Now that we have it, we can plug it into our enantiomeric excess equation. So how much more of one enantiomer do you have? Well, that depends on how much it's rotating the light. The more it rotates the light, the larger percentage it takes up in the mixture. It rotates the mixture is rotating the light 2.23 degrees to the right. If it were 100%, it would rotate the light 2.8 degrees to the right. So what percentage of that is 2.23 of 2.8? 2.23 divided by 2.8 times 100 gives you around 79.64 degrees. I'm sorry, percent. 79.64%. You have around 79.64% more of one enantiomer than of the other, more of the L-alanine than of its enantiomer. And note one last time that that is not the absolute amount. That's not how the percentage of L-alanine in the solution. You have this much more. Just to think about this a little more clearly, let me round it up to 80. You have 80% more of one enantiomer than of the other. There's still another 20% left in the solution. But that 20% isn't rotating the light. Only the 80% rotated the light. So that other 20% must have canceled itself out, and the only way it could have canceled itself out is if 10% of it was the L-alanine, but the other 10% of it was the other enantiomer, so that they cancel each other out, and it's only 80% that's rotating the light. But that means that the total amount of L-alanine in the solution is 80 plus 10, or 90%. 90% of the solution is L-alanine. We have 80% of that enantiomer in excess. We have 80% more of that than we do of the other enantiomer. So this is one way you can get, if you have a mixture of enantiomers, you can use this concept of enantiomeric excess to figure out how much of one enantiomer you have. And it can be really useful because a lot of times some molecules will switch between their chiral centers, so you can get a sense of how much of each one is present. And a lot of times in reactions, the products you get are mixtures. So it's really useful to know about what percentage you have of one mixture and of the other, and you can get a sense of that